Hi guys, this is Kunal, and today I am going to discuss uh, the topic called linear regression uh, with one of the case study called bike sharing. So let's understand the problem first. Basically, we will build one multilinear regression model to predict the demand for the shared bikes. But the problem statement is a bike sharing system is a service in which bikes are made available for the shared use to individual on a short-term basis for a price or free. Many bike share system allow people to borrow a bike from a dog, which is usually a computer control wherein the user enter the payment information and system unlock it. The bike then can be returned to another dog belonging to the same system. Uh, let's understand the business goal. What we are trying to figure out. We are or we want to achieve from this task. So we will build one model for the demand of the share bike with the available independent variables. It will be used by the management to understand how exactly the demand vary with the different feature. They can accordingly manipulate the business strategy to meet the demand level and meet the customer expectations. Further, the model will be a good way to for management to understand the demand uh, dynamic for a new market. So basically, we have to build one linear regression model called multilinear regression model for the bike sharing problem, where a management want to understand what are the independent variable uh, uh, what are the independent variable they would be interested, and they can manipulate to maximize the business or maximize the sale uh, according to the analysis or according to the model. So let's go and let's try to understand the problem. And so here, if we try to understand the data, so we have some data dictionary here. So basically, we have a instant, a record index, and then we have a date, we have a season, and that is called given 1 2 3, and we have a year for 2028 and 2029. Then we have a month from 1 to 2 on to 12, holiday whether it's a holiday or non-holiday, and we have a weekend, it's a weekend or non-weekend, and it's a working day or non-working day. Then we have a temperature, and then we have a temperature, filling temperature in the Celsius. We have a humidity, and we have a wind speed, and these are the casual user, and we have a registered user. But if we go here, we have a count. I mean, the count is for total rental bikes, including the people either it's from register or from the casual user. And then we have a weather situation. It could be clear, it could be mist, it could be light, it could be heavy. So these are the data we have, and now, so we have divided the task into the multiple section. That section is called, first of the section we are going to deal with the data reading and understanding. So for every machine learning algorithm, first we have to understand the data, and see whether data can be in standard format or not. Do we have a null value, or we have to clean the data, or we have to transform the data? Do we need to derive the other field? And we also need to understand the, like, we have a multicollinearity among the user or not, or whether it's a linear or not. So we will try to understand all those things as a part of EDA. And so before doing the EDA, we have to make our data ready. That's using that uh, the information we can perform the EDA. So let's understand the data, and if we need to change it, we'll transform the data accordingly. So if we go through the, we are reading the data here, and if you check it here, so we have a here instant number, it is a numeric value, and then we have a date, so it's a one kind of a date. We have a season, so we have already mentioned it here. So we have a season, 1 for spring, 2 for summer, 3 for fall, and 4 for winter. So we are having in a numeric format. And then okay, here, so 0 for 2020 so 2018 and 1 for 2019. Then we have a month, so it's a from 1 to 12. And then we have a holiday, basically it's a 0 to, it's a 0 or 1. It's a, if it is a holiday it's a 0, it's non-holiday it's a 1. And then we have a weekdays from 0 to 6. Then working day, whether it's a working day or non-working day. Then with the situations 1 2 3 and 4. And then we have a temperature, so we can see then we have a feel like temperature, then we have a humidity and speed casual, register and count. So here the count is the sum of casual and registered column. So here we, let's check the size of the data. Here we have a 730 row and 16 columns. So now we will start we have to go through the data, understand if there is any kind of null values or not, or we have unnecessary data or not. So let's see if we have a header, footer or summary details row. So we are trying to see its head, that we have already done it here. And so head will give that we are trying to see if it is here header or summary details or not. And now we are checking with the tail, so there is no subtotal or footer rows here. And so from web analysis, and then we are checking here do we have any null values or not. So if we try to see it here, we are having 730 row as a non-null for each of the columns, and we have a total 730 row. In a more general way, for each of the fields we are doing edge null and sum, so it will give me the number of the null value for each of the columns. So here we can see that there is no any null value present in any of the column. So it seems that our data is clean. Here we are seeing the permissible range. So we are seeing, so it is a instant, it is a numeric value, and we can see that its count is 730. So basically it is a unique value. Then we have a season, so it's a 1 2 3 4. We can already see that. Year, it's a 0 and 1. Month 1 to 12. Holiday, weekdays, so 0 1 2 5 6. Working days, 0 and 1. Weather situations 1 2 3 4. Temperature, it seems from 2 to 35. Feel like temperature from 3 to 42. Humidity is a 97, 0 to 97. Wind space 34. Casual count 3410. Register 6. So here we can see that we are not able to find any kind of outliers here. So data is much clean here. And there are some other observations we can see that here. So if you check it here, ddate is the only field that have a value as object. Either all are int or float. I mean other data are numeric except ddate. And we can also see that we are having month and we are having the year. So we can remove the ddate object from this data. So let's try to see what are the, we have already figured it out, there is no null value present into the any of the columns. And let's figure out what are the columns which is unique in the nature. So we have find out one is a instant, other is a ddate, that are unique into the feature, and the column which values are unique into the feature. It doesn't make any it doesn't make much differences as a part of our EDA analysis or when we are developing the machine learning algorithm. So it's better to delete or drop those columns. So here we will be deleting the instant and the ddate columns because it doesn't make any difference for our models, so that we can remove uh, those columns from the analysis. And here we will check if there's a duplicate or row or not. So duplicate row is 0, so no need to delete it things, and no unique. We don't have any unique value present. Now we have noticed that like a season, with a situation, and month, all are the categorical data, but they have a converted into the int. So now we are trying to convert back to the categorical data here. So as per data dictionary, year has a two value, 0 for 2018 and 1 for 2019. Holiday 0 or 1. So if it is a 0, it's my holiday. 1, it's non-holiday. Working day, it's a 0 or 1. Weather situation has 4 values: good, moderate, bad, and severe. So we are trying to match. We will trying to convert those, since it is a kind of a categorical values only. So what we'll do, we'll convert the numeric to the categorical value. So here we are replacing the numeric to the categorical value, and for the season, either for weather situations, either for month, and here we are for weekdays. So now what we are trying to do, so if we check it here, so all that data has been uh, converted from numeric, not all the data. So respective numeric value has been converted to the categorical data. So if you check it season, we are not converting year to uh, in categorical data type, because we have 0 or 1, and month we have converted it. Holiday we are not doing as a 0 and 1, it's a binary value, and we have weekdays, and here it's also a binary value. With the situation we have converted it, and okay, so things looks good here. So now we can perform the EDA because our data looks clean and within the range, and there's no any outliers presented here, and all the data in proper format. So as we have already discussed as well, uh, as a part of EDA, there are some steps we perform. One for univariate analysis, uh, other is bivariate analysis, and then multivariate analysis. So as a part of univariate analysis, we try to understand the distribution of the data, uh, ranges of the data, mean value, max value, and how the data is distributed. If it is a numerical value, and if it is a categorical value, we see that what are the counts coming for categorical data. So categorical could be either it's a order or non-order. So first here, if we check it from the data, like we have a temp, air temp, humidity, wind speed. These all are numeric value. So for numeric value, when we perform the EDA, and when we try to perform EDA for invariant analysis on numeric value, we generally draw the box plot or distribution plot here. So for each of the value, I'm drawing the box plot. So using the box plot, I can easily see that what are the minimum value, what is the maximum value, what is the median, what is the 25 percentile and 75 percentile for each of the values. And it looks good for me, as we have already seen it here as well. And here I am drawing the line graph for our target value or target variable year for 2008 and 2019 with respect to the month, so that we can see how the sale has been progressed from January to February and for each of the year. So the blue line represent uh, for 2018, and red line represent for 2019, and we can see that the sales has been risen from 2018 to 2019. So there is a clear growth we have from 2018 to 2019, and we can also see that if you check it here, basically June and October, we have around highest number of the sales. So from this diagram, what are the inferences we can figure it out? So from line graph, we can see that the target variable count has been increased from 2018 to 2019, and demand for bugs is high between May to October for 2018 to 2000 for both of the year, and bugs are there's no outlier present. So these are the things we have captured the details from the as a part of univariate analysis, and this is we are drawing the pair plots uh, for understanding the dependency between the independent variable or numeric variable here. So some of the reference we can count it that if you check it here, the attempt and temp are highly correlated to each other. Uh, it means that attempt has been derived from the uh, temp, temp variable, and we can also see that there is some okay, and we can also see that the temp or attempt is depend on the account variable. See, we can see that there is a linear dependency between the attempt and temp on count variable. Now we are going for bivariate analysis. So bivariate analysis, why we do is because we want to understand the dependency between the target variable and independent variable. So how the independent variable affect uh, our target variable. So here two variables, we always compare two variable, uh, that always the one variable is always a target and other variable is a independent variable. So let's try to and we are trying to what we're trying to do it here is we are trying to do the bar plot. We generally do bar plot for the categorical data, okay, and see how uh, it is affecting the target variable. So from here we can see that if let's do one by one. So if we go it here, so we have done for numeric, we have done univariate analysis for numeric variables, and we have drawn the pair plot uh, for numeric variable for bivariate analysis. And then here we can see that okay, uh, so season is one of the categorical variable. So we can see that the bike rent is high uh, on the season of fall, and compared to 2018 the sale has been increased uh, during the 2019. Also from month we can see that from May to October have a high number of bike rentals, and if we compare with respect to the year, so the bike rental has been increased throughout the year. And then we have a weather situation, so we can see that if the weather situation is good, then we have a high number of bike rental. If bad, uh, we have a low number of uh, bike rental. It means we can also say that it is having some negative correlation between the weather situation, having the negative correlations between uh, not negative, we can say that if it is a good, it will increase, if it is a bad, it will decrease. And of course with respect to the 2018, uh, it has been like a bike rental has been increased. And weekday, if we say that Sundays having the lowest number of bike rental, means people do not prefer going out uh, on the weekend. And then holiday, so if it is holidays one, then people are not preferring it. And here if you see the count here, so if it is a non-holiday, uh, basically people prefer bike rental on non-holiday. If it is a non-working day, if it is a working day, so if it is a working day, uh, I mean people do not prefer go out on the non-working day. And here we are trying to see as a, we call as a multivariate analysis. So multivariate analysis, we are doing the heat maps or correlation matrix. So here we can see that if you check it, attempt and temp are highly correlated with each other. It means that it has been derived from one of the, so we can drop one of the variable or feature as a part of machine learning while building the machine learning models. There is also some highly correlation between, we can see that we have a casual, registered and count. So it means that we already know that the count is the sum casual and registered, so we can delete casual and registered feature as well. And here is having a good dependency on count. Registered we have already sent, okay. And we can also see that humidity have a negative correlations on on the count. And we can also see that holidays have also having the negative correlations on the count. Okay, so some of, we can delete it from here also, but what we are trying to do that we are trying to do some of the feature will try to drop while doing the analysis using the VIP and REF. Dropping casual and registered as they are sum to the count. So here we are dropping it. Now we are trying, now the next step, since we are done with the EDA and we understand the structure of the data and what the data are in, like are dependent on or linearly dependent on the on the count variable, and what are the, is there any collinearity between the independent variable. So we have understand all those things, and now we are trying to move to the data preparations. So as a part of data preparations, since we are having the sum of the categorical data type, now we need to convert into the numeric data. Okay, so we have to convert into the get dummies because this is a categorical data. So for categorical data we have to convert into the get dummies. And there's one rule for dummy variable. So if any dummy variable have a n value, then we need n minus 1 column to represent that one. So that is the reason we are using draw first. So it will drop one of the first column when it will try to create the dummy variables. So 10, 10, 10. Okay. So here we can see that already we have already created a season, false, month number, December, weekend, Monday, Saturday. So we have already created a dummy variable for it, and only one of the field is one of the value is going to be enabled corresponding to those values. So once we done, here we have to split the trained data and test data. Before performing any analysis further, we have to divide the data, and we need to, yeah, we need to divide the data into test and trained data. So as a rule, around 70 to 80% we put into the trained data, and 30 to 20 to 30% we divide as a part of test data. So now we have to since if you check it here, just go there. So if you check it here, temperature is having as a value 14, 1, 18, 0, some value are low. Here registered value is equal to, or count value, or sorry, yeah, registered or count is 985 or something, right? So one of the feature maybe uh, uh, can have a high impact on other feature. So we have to convert we have to convert we need to scale those numeric value, so that within either two way, either is using the standard scaler or min max XLR. So in min max we are having a 0 to 1, so that one field doesn't have a high impact on all other fields. Okay, so we can see that here as a part of here we are. So here there is one more point I like to discuss it here. So here if you check it here, these are the numeric variable, and we have to scale those needed. We will scale those numeric uh, uh, variable using the min max scalar. So min max scalar, what will do, it will convert all those numeric value between the in the range of 0 to 1. So it will have a very low impact if some values are high, some feature variable are very high, and some other feature variable are very low. So it doesn't create much gap on that part. So that is the reason using the min max scalar. Other way we can use a standard scalar as well. And here uh, we are using fit and transform. So fit and transform, it will learn the data and understand what is the minimum value, what is the maximum value, what is the mean and median, and then transform it. We have to note it down here. We only use fit transform on the trained data. We do not perform into the test data. So if we perform on the test data, then the model will try to learn from the test data as well and understand what is the minimum, maximum, or median value there. And we have an issue with the data leakage. And so we will consider test data as unknown data to the model. And for that reason, we will not use the fit transform, we will only use transform method. So here we can see that all the values has been scaled between 0 to 1, and we can perform the we can also draw the hit map matrix or correlation matrix to see if there is any dependency between linear dependency between independent variable or not. So we have already identified that we have a temp and attempt as a these are highly correlated with each other, or multicollinearity. We have to remove those feature. So here we are popping out a count variable because count is our target variable. So we have to convert into the x and y part. So we are saying as a count as a y train and rest of the data as a x train. And first we'll try to build using the stat model using all feature. And okay, so here we have a build using the stat models, and here we can see the list of the parameter and the corresponding coefficient. So as a part of linear regression, we generally try to train a model or find a line and figure out the coefficient of each of the variable and the constant that will give us the best fitted line. So here we can see that r squared is equal to 0. So when we are building the any linear regression model, any model, we have to check the accuracy or how the what is the coverage of features uh, into the model. So we can see that the feature we have used it here, it covering around 85% of the data. And since r square may not give the correct uh, value, so we are using the adjusted r square. So if it is a multilinear regression model, we will be mostly focused into the r squared, because there is one issue with r square, that if we add features, either it will be constant or it will improve. If some feature has a negative impact into the model, it will not decrease the value. That is the reason we will use the r square, because r square is compensated with the adding the variables. So this is the one. And so basically we will while building the linear regression model, basically we will be focusing on two things: adjustment r square and the p-value. So we have to check for p-value for all the features. If p-value is greater than 5% or 0.05, then that feature is insignificant and we need to drop it. So there are two ways to dropping a feature, either using the p-values and other is a VIF. We'll discuss into the later part. So as of now we can see that adjusted r square is 84%, which is a quite good, and it could be a good starting point to build our model. And we'll try to see that if we can eliminate some of the feature that doesn't have a significance role into the our models. To eliminate it, we will following there are two approach. Either we can use REF or we can do the manual feature elimination. So REF is nothing but it's a RFE, so recursive feature elimination. Here we have to give the number like how many features we want, and according to that it will give the top feature that is going to that will contribute to our model, and it will remove the other non-significant feature. RPF could be a little tricky and we might be losing some of the important feature. So what we'll do, we'll perform some feature eliminations using the RPF, and for some part we'll use a manual feature elimination. For that part we'll go step by step. So we will use a hybrid approach for feature eliminations. So let's here we are building we are running a RFE model with 15 features. So we are creating linear regression model, and we are fitting here X trend, Y trend, and then we are creating the RFE with estimator as a, we are passing as a linear regression model, and the number of feature to select as a 15. Here we have already passed our train data and train data. So what it will do, it will fit the model and give us the model which is having what we call a 15 important feature, and rest are insignificant feature. And so what are the feature we have that has been significance feature, that will mark as a true. So if we check it here, true, so all the significance feature value will be true, and the third value will be marked as a 1. For insignificance feature, the second column value will mark as a false, and it will also assign the priority based on the significance. So if we check it here, so we can have a big day Thursday, which is having the priority as a 13, it is having 14, it is having the 15. So those are insignificance field that can be removed, and RFE will remove it while building the models. So here RFE support, it will return the feature which is significant for the model, and RFE support negation will return the feature which is insignificant for the model that it has calculated. So now we will start building our model with RFE support feature. I mean that is a significant to our model. So now we have a 15 mod. We have provided our number as a 15, and we'll see one by one how much feature we can eliminate. So now we are using now okay. So now the feature here we are capturing the columns that we are going to use to build our model, and extend RFE is a list of feature that we have just obtained from the RFE model after eliminating an insignificance model. So the number of feature here, it will be 15, earlier it was at around 30. Now we are going to build the second model. So as a part of first model, we have removed or we have eliminated 15 insignificance feature. Now we have a 15 significant feature, and gradually we'll try to eliminate one feature one by one and see how the elimination is impacting our over like a it's impacting our the machine learning model. To eliminate the insignificance feature, we have to use p-value, and we also need the VIP value. So for VIP we have written here the one function. So if you pass the data frame, it will return the VIP value for each of the feature. So here we can see that if you check it here, so working day is having a VIP value is 31.53. So there is a one rule we have for VIP. So generally, if the value of VIP is more than 10, we have to eliminate those feature because that will become the insignificance. Other rule that if we have a some value is less than 5, that is significant, and between 5 to 10 we need to scrutinize that. I mean, we need to perform the analysis on that whether those feature is useful or not. So 5 to 10 should be much, this should be more careful. And then okay, so here we are trying to build a second model. So we will be using the SMA add constant. We have to add the constant while building the model using the stat model, and we are passing the latest feature that is capturing as a part of extend RFE, and then we'll create a new model here, and then we can get the summary here. So this is a summary of the latest model that we have obtained from the latest 15 features. And after removing those features, we can see that we don't have much differences into the adjusted-r-squire, and that is the one part. And we can also see that okay, this is good, and if you check it, we have to see whether the p-value is greater than 0.05 or not. If it's 0.05, we have to drop those values. Here we don't have any 0.0 greater than 0.05 for any of the feature, so we are not going to read from here. What we have to check, we have already checked that. So there is one rule. First we need to always check whether the pi value for one of the any of the feature is greater than 5% or not. If it is a 5%, we have to drop it, but first we have to pick up the value which is having the highest p value. So here we don't have any highest p value. If not, then we have to check VIP value. We have to pick the VIP value which is greater than 5. So here working day is having the 31.53. So what we have to do that we'll remove one feature one by one and see the impact. We will not going to delete all the feature whose VIP value is greater than 5. So here we'll drop one feature and see how the impact is happening on the rest of the models. So here so in the next step we are going to drop the working day, and we'll after dropping the working day, we are going to have a number of feature is equal to 14 because we will drop it, and we will calculate the VIF on the rest of the feature. So here humidity is the high. After removing the working day, we see that humidity is having the highest VIF value around 14.57, but we will not delete it. First we'll check the p value of the model that we have obtained after deleting the working day. Still, that should be always, we have to always check whether the adjusted R is improving or it is going down. It should not go much down. As for a rule of thumb, we can go from, it should be around, if it is greater than 80%, this is good, but if it is less than 75%, then model is not good. So we'll try to build a model which adjusted R value is greater than 75% or more than 80%. So this observation we always have to keep into the mind, and then we have to check whether the p value is greater than 5% or not. So if we check it here, weekday Saturday is having the p values around 48%. So first we'll have, so now we have a 2 point. Weekdays Saturday is having the p value as 48 point, like a 48%, and VIF for humidity is having the 40.57. So if there is a such scenario, then we'll always choose the p value first. I mean, first we have to remove these features. So here we are deleting the weekday as a Saturday, and after that we'll again check. We are obtaining the new feature set, and based on using the new feature set, we'll calculate the VIF and check. We are not deleting. Humidity is still 14.6, 14.46. Now we have to check whether we still have some p value is high or not. Here we don't have any p value whose percentage is greater than above than 5%. So what we'll do, we'll remove the humidity feature from the models or feature list. So after dropping, yes, again we have to build we have to calculate the VIF. Now we have a temperature 5.53, and then we have to we are calculating the VIF, and then we also calculate the OLS, and we are going to see if it is still it's quite good, but there is no any p value. Okay, so one thing I want to discuss it here, since we have already checked the temperature that is highly correlated into with the count. If you check it here, temp is highly correlated with the count. This is temp is highly correlated with the count. So will not be dropping that one, and I have already tried to remove it, and the adjusted-r-squire values was dropping around 65%. That was impacting a lot. So since count is dependent into the temp, so we will not dropping those feature. And yeah, so if we check it here, so yeah, so we don't have any value whose p value is greater than 5%, and apart from temp, we don't have any other value whose VIF value is greater than 5.53. And since temp is correlated, highly correlated with the count variable, we are not going to delete or drop these features. So now we can see that we are having the 11 feature, 12 feature, and we all need those feature to build the model. Okay, so before building or before testing our accuracy, we can use that. We have to prove some linear assumption. We have to perform some linear regression assumptions proofs, because when we are doing the linear regression model, there are three rules that we have, there are three assumptions that we have to prove. So let's perform some residual analysis to prove the assumptions. So first assumption is called error distribution. So error terms will be distributed across the 0, and that we can see that here. So our error term distribution is centered around the 0 mean. So that we have already verified it. And the other assumption that error term being independent. So we are not able to find any pattern among the error term. So this is also, I mean, there is no relation between the residual and predicted value. So this is also satisfying the second law. And third is called homoacidity. I mean that there shouldn't be, uh, the variance across the error term should be a constant. It shouldn't be like we don't have either conversion or divergence on in any of the point. So all satisfying the rules here, and we can draw the heat map X here. So we do not see any multicollinearity. Why we are doing that? Because we have to check is there any multicollinearity still there into the feature variable or not, and we do not find it. So now we have to perform the predictions on our test data. So now we have to also prepare the test data, and as a part of preparations, what we have to do that we need to, first of all, we have to separate the x and y, and after separating the x and y, what we are doing that there's one thing, test and y describe. Okay. Here we are transforming the data using the scalar, I mean min max scalar, and converting the data between the range of 0 to 1. So that part is it. And here we are, as I have already discussed, we will not use a fit transform, because we don't want our model to learn the test data. And if we use fit and transform, it will learn the data about the minimum, maximum, medium value, and it created the data leakage problem. So that we don't want it here. For our model, the test data should be always unknown. And here describing the data, cutting the x and y into the different sections. And here, since here we have a list of features, we have already built the model, so we will be using those features only, and we are building the, so here we can see the constant variable. Okay, so now generating the R square. So if for R square between the test, we have seen 7.77, and train adjusted R square is 0.84, and train R2 is equal to 0. So here we are getting from the adjusted R square. Okay, so R2 square we are getting around train adjusted R square of 0.84, and train R2 0.844, and R2 score 0. It's around 78%. Okay, so here we can see that adjusted R square is 0.83. So test, if we check it here, the test adjusted R square and train adjusted R square. So train adjusted R square we have a 0.84, and test adjusted R square we are having 0.83. That is if try to find the differences between them, it should be less than 5%, and it's around, we don't have much differences, around 1% or 1.5%. So this model is good, and the final equation we can achieve using the we have to put those coefficient that we have learned from the model. So basically these are the coefficient we have to replace for each of the this is the features and this is their corresponding coefficient. So basically we have figured out the coefficient and then we have to replace the coefficient for their corresponding variable, and based on those value it will always, this model give the predictions. So this is for today, and I hope if you have enjoyed our session today. That's all.